that's if f is continuous. And finally, the third is if it's bounded and piecewise continuous. So that covers a lot of examples. Did anybody come up with an example of a function that is not integrable, that without having an asymptote? Obviously, if it's unbounded, then there's going to be infinity involved. Yes, Teddy?
The function where it's like if it's 1, if it's rational.
Yeah, right, exactly. F of x equals 1 if x is in the rational numbers, which I think Q is the symbol for rational, or quotients, and 0 if x is not in Q.
That's going to be a problem.
So let's just take a look at that function.
No, it
You
is.
can't
If I
draw it.
sit.
It looks like two horizontal lines.
Okay.
It's just got lots of holes, and the holes in one match up with the points in the other. And let's take it from anywhere to anywhere. Let's say from 0 to 8. Let's try to do the integral of f of x dx for that function from 0 to 8. And here's the problem. You see, what made the key here about monotonic and bounded, the key there was that we can take the upper Riemann sum and the lower Riemann sum and show that the difference between them, that error that slides into that one vertical rectangle, that goes to 0. And that means that upper and lower have to have the same limit. And if they have the limit, then obviously all the other Riemann sums have to be between upper and lower. They'll have the same limit. And that's what we need. We need that limit as n goes to infinity. Remember this definition, limit as n goes to infinity of the summation f of x sub k star times delta x as k goes from 1 through n. We need that limit to not only exist and be a finite number for some Riemann sums, but for any Riemann sums. And if upper and lower have that same limit, then the others are sandwiched. Okay? Everybody okay with that? Now, why does this fail? Well, what's the upper sum? Divide it into as many pieces as you want, and in each piece, your upper value is 1. And if you take 1 times that delta x and add them all up, you're going to get a total of 8. The upper sum for any n is going to be 8. And the lower sum for any n, no matter how tiny you make these intervals, every one of them has both rational and irrational numbers in it, right? And every one of them has y values that are 1 and y values that are 0. And so for the lower sum, you can always be taking 0. And if you add up all those zeros, you're going to end up with 0. And that's true for all n. So therefore, the limit as n goes to infinity for the upper sum is 8, and the limit as n goes to infinity for the lower sum is 0. So they disagree. And all it takes is for any two to disagree, and you do not have an integral. Who knows what the other ones would do? Left, right, etc. It doesn't matter. If you can't get them all to have the same limit, then it shouldn't depend on which Riemann sum you choose. And obviously in this case it does. But that's a weird function. I mean, anything that you can write a normal equation for is going to fit here. It's going to be, maybe have a few asymptotes that you have to avoid, but if you take any interval that avoids one of the asymptotes, the function will have some finite number of ups and downs, and you just break it up into each of those separate sections. It's bounded and monotonic on each of those, and the total integral is the sum of the integrals of each of those pieces, and you're good. So you will have an integral everywhere except where you have an asymptote, or if you have something really weird going on like that. Okay? All right, good. Now let's talk about the relationship of differentiability, continuity, and integrability. We already had what relationship before between differentiable and continuous? Which implies which? Differentiable implies continuous, right? Not the other way around. You can have a continuous function with a corner or a cosine. But if differentiable, then must be continuous. Where do I put integrable into this? How is it related? Well, it's up on the board, isn't it? On the smart board. If continuous, then integrable, right? So that means that the set of all differentiable functions is a subset of all continuous functions, which is a subset of all integrable functions, right? In this region, you've got functions like the step function that are integrable even though they're not continuous. Here you've got things like the absolute value, which are continuous even though they're not differentiable. Integrable is the widest class of functions. That's why we've got to really search hard. That's why it was a challenge last night. Find me one that isn't, all right? Without doing the obvious, which is a vertical asymptote. And differentiable are the smallest. If you've got differentiability, you got everything else. You got both of the others. All right, so that's another thing. Now, I want to just do a few odds and ends before we get on to the main idea today. So here's another one. Let's take another look at average value. You'll recall, what's the average value of a function f on the interval AB? How do we define that? 1 over, go ahead. Is this it?
Yeah, integral
From A to B
over interval b, or sorry, yeah, f
of f of x dx
over b minus
over b minus a, or we sometimes just put the 1 over b minus a. Yeah. Okay, good. And we saw a couple of good reasons for that. And one was this idea, I mean, again, we've got this function over here, and we're looking for the average value. What we're looking for is a function that accumulates just as much as the function does, which means the area below this line is the same as the area below the curve, right? And we gave the example of velocity. If I was traveling at average velocity and you were variable velocity, we should, if my speed was your average speed, we should cover the same distance in the same time. Okay? And another way of saying that is you can think of this as like the center of the waves, with that whatever is below here accumulated should match what's above here. You know, what the part that's above the line from the curve, the area is going to be the same as what's below. Okay. But let's go back to the original idea. I mean, you might be convinced by these, and I think they're reasonably convincing arguments that that's why you would take that. But let's also think about when we average things. What do we usually do when we average things? We just add them up and divide by n, right? So we'll just sample some points. We'll sample some points. Now, I want to sample them fairly because I'm going to increase the number of points. I mean, I can't sample infinitely many. But if I sample more and more and more and take the limit as n goes to infinity, that should give me an average that's better and better at covering the whole crazy scope of this varying function, right? So I'm going to get the summation of f of x sub k. As k goes from 1 to n, I'm going to take n different values, and I'm going to average them, so it means I'm going to add them up and then divide by how many points I use, which is n. And then I'm going to take the limit as n goes to infinity. That should give me the average value, right? I'm taking the average value of more and more and more points. And that's what I mean by the average value, yeah? Well, of course, I have to divide these up carefully, because I can't just increase the number of points by putting a whole lot of more points here. I've got to make sure they're spread out. So I'm going to spread them out equally by taking each separate section. When I have n, I'll divide the interval from a to b into n equal pieces, and I'll pick one from each. So that's x sub k star, something randomly selected from the kth interval. Is this starting to look familiar? All right. Now, b minus a is a real number, which is not 0. So we can just multiply and divide by b minus a. So I'll divide by b minus a, and I'll multiply by b minus a. It's not affected by the limit, so I can put it inside there. It's not affected by the changes of k, so I can put it inside there. So there's b minus a. And then this n on bottom is the same as having a 1 over n in front. And n is not changing. It's where we stop. But it's not changing with k, so it can go inside. So I can put the 1 over n inside. And what do I have? I have 1 over b minus a times, this limit is the integral, isn't it? This is the limit as n goes to infinity. Summation k equals 1 to n. F of x sub k star times, that's what delta x is, isn't it? It's g minus a over n. So here's a nice way of seeing that it's exactly what we would call the average value. You would average all those values if you could. Well, there's infinitely many, so you got to use a limit. And you're getting exactly what this formula gives you. All right. So, next thing. Again, I got a few little odds and ends. Remember the mean value theorem? Yeah? Says that somewhere along the way, your instantaneous rate of change matches your average rate of change. Well, there's another theorem that you need. and it's called the integral form
It's a big decision.
of the mean value theorem.
Can't tell what is.
And the integral
Let's
form
read
of the
those
mean value
two.
theorem says that if f is continuous on the interval AB, then there exists a C between A and B such that f of C is equal to 1 over B minus A times the integral from A to B of f of x dx. What did I just write on the right-hand side? What is this? Yeah, that's the average value, right? How is this the integral form? Well, it's got integral in it. Well, what's it got to do with mean value theorem? Well, in the mean value theorem, you were saying that the average rate of change, f was the function whose rate of change you were looking at, and the average rate of change is that slope, and you're saying that somewhere in between the instantaneous slope matches. That you match the average rate of change. Now you're matching the average y value. Now in this picture, f is some function like that, and we're matching the average y value. We're saying that, hey, if there is an average y value, somewhere along the way you're going to meet that. You're going to have that as your y value. Just like here, the actual slope at that instant matches the average slope, the average rate of change. Here, an actual y value is going to match the average y value. Well, what's the average y value? It's somewhere, obviously it's below the maximum, right? And it's above the minimum. Somewhere in here is the average y value. And I may not have drawn it right. If I drew it right, the areas below and the areas above should be equal. So I think I have to move this one down a little bit. But anyway, it's below the maximum value and above the minimum value, right? So that's the average y value. And how do I know, in this case it looks like there's a few places where that happens, how do I know that there's got to be at least one place, C, where the y value matches that? What property of the function am I using? Continuous, yeah.
There we
It's
go.
actually a combination using the intermediate value theorem, right? You know you've got this and you've got that somewhere in between them. Somewhere between, so this was, you have at the maximum you're above the average value. At the minimum you're below it. Surely somewhere in between you have to cross it because the function's continuous. Notice we don't need differentiable here because we're not doing derivatives. We just need continuous. And f continuous also guarantees that the integral exists. So we use it twice. It guarantees that the integral exists so you'll have an average value. And secondly, it guarantees that you've got to cross it because of the intermediate value. Alright, so that's the integral form of the mean value theorem. Yes?
The C can be inclusive A and B, not extra.
Yeah, again, I'm a little bit, usually you'll find it interior, but yes, it could be. All right, so, then the next thing I wanted to talk about is area. Well, we've been talking about area, sort of. Remember I keep saying we've got to put quotes around area? You know? Because we allow it to be negative if it's below the axis. If we're going left to right, or for that matter, if we're going right to left, then the stuff above is negative. So, what if we really just want area? What if we want, for instance, here's the function 9 minus x squared, and I want f of x equals 9 minus x squared, and I want the area between that function and the x-axis. I want the area between f and the x-axis on the interval from 0 to 5. Alright, so let's look at that. So it's crossing the x-axis at 3, and here's 5. So, let's cross it down here. So this green stuff is what I want, right? That's the area between my function and the x-axis on 0, 5. So that would be the integral from 0 to 5 of 9 minus x squared dx. True or false? is that integral the same as that area?
False.
False. Again, area is, that's why it's not really the best word for integral. It's accumulation. What's the difference between that integral and this area?
Part of it's
You said false, so how are they different?
Because the lower area is going to be negative,
Yeah.
and it subtracts.
And it'll cancel that. I might even end up with a negative answer, but even if I end up with a positive answer, it'll be smaller than the actual area because I've canceled parts of it. True area is positive and does not cancel. That's why I always sort of put quotes around area when we talk about the integral. So how do you actually write an expression for the area? So this is false. That's not the area. That's the accumulation. Now, there are two ways to fix it, one of which you're not allowed to use on the AP. Okay? You can just put an absolute value on 9 minus x squared. They will say, write an expression for the area not using absolute value. And another reason, by the way, if you're going to use the numerical integral, absolute value slows things down. Okay? But they really want you to show that you will know what that is doing for you. So what is the absolute value doing for you? It's making you count this positive and count that positive also. So how can we do that? Just split it into two parts, right? So the correct answer is my integral from where to where?
0 to 3.
0 to 3 of 9 minus x squared dx. And then add on, what?
5.
From
Negative.
3 to 5, but I don't want it to count negatively, so I have a couple of choices.
You could do
I can
5.
change that plus to a minus, or I can leave it plus and just switch 5 and 3. If I'm going to the left, that'll make it count positively. Or I can change the 9 minus x squared to an x squared minus 9. Just don't do two of those, because then you're back to counting it negatively again. All right? Do any one of
Or you
those.
can do all three.
Keep it simple,
God.
right?
Don't you
So
dare.
keep going left to right. Keep the function the same. Just change that to a minus to make this count
That's
positive.
what
All right?
I like that.
All right, so that's it. That's all you need to know about area. Be careful about that on the homework. You have to show that, and sometimes you have to do some work to find out where it crosses. It might be something where you need the calculator. Remember our 4 tasks that we're allowed to use the calculator for? We now have the 4th task. Okay? One task that you're allowed to use the calculator for on part 2 to show work is they give you the equation, they give you the window, you show the graph, right? Each of these is just worth 1 point. A second task is you solve an equation. So you just write the equation down, you write the solution, right? You don't say which buttons you're pushing, you know, how you solved it on the calculator. You just write the equation, write the solution. If it's a calculator okay question, it's clear that's what you did, and that's all you've got to show. The third one is a derivative. You just say which function that f prime of 7 equals negative 20.384 or whatever, you know. You just write down what the function is derivative at what point equals. You don't show anything else. Again, you don't write n deriv or anything like that. And same with integral. You're not going to write finite, right? You're just going to write. So if you had to solve the equation, in this case it's obvious, but if you had to solve it, you would just write the function equals 0 and then get that point, whatever that decimal was. And then you would take the integral of that function from 0 to that place. You would just write this, and below it you would write the decimal, which is the answer. That's all. That's all you write. Okay? You do not do anything to show what buttons you're pushing, because they're specific to different calculators. And they're not the point. They're the how. What you're doing is getting the integral. You happen to be using the calculator. That's all. Okay? So, that takes care of that. Are there any questions so far? All right, one little comment. Some of the questions on the homework give you a rate of change. I want to remind you that the integral of a rate of change is the amount of change. Starting with our first trash example. The function was the rate of change, the rate at which trash was accumulating, right? Positively or negatively. And to find out how much trash was in the dump, you took the integral from A to B, and that's the amount of change. That's the amount of trash extra in or out from where the dump was at the beginning of that. So I just want to remind you of that, because it shows up in a couple of different contexts. All right, now, I believe that we're ready for a couple of homework questions, if you have any. And and then we can go on to the. I want to make sure by quarter up to get to the new thing that we're going to do. The big thing. All right. Yes.
So on 21, the actual problems themselves are not that hard, but they change.
This is from the book.
Yeah, no. This is from the packet.
The packet. Okay. Which question? 21 on which section? Section what?
No, it's from the book, page 379.
All right, you just want to mess me up. Okay. 379, number 21. So, yeah, you want to show, you're given that f is continuous, and that's using those theorems. So that's getting back to those theorems we talked about yesterday. Which one of those you want me to do for you?
No, I could understand, but why did they? I didn't understand why they changed it from like x to u to z.
To show you that it doesn't matter what variable it is. That x is a dummy variable, just like if I have a summation. The summation k equals 1 to n of k squared is the same as the summation j equals 1 to n of j squared, is the summation of w equals 1 to n of w squared. All that matters is where it starts, where it ends, and what the function is. That's true for summations. An integral actually is a kind of summation. It's just one that we've done a limit to. So all that matters is where it starts, where it finishes, and what the function is. The name of the variable is irrelevant. Okay? So they did that specifically to let you know that. Okay? To remind you. Yes, Tracy.
Can you go over 22 on the packet?
On the packet, which section? C?
Yeah.
Okay, C22. So supposing f is graphed in that picture there, and roughly that looks like this, and then like that. And this is 5, and this is 2, and this is negative. And it says, any particular parts of this question?
Oh, wait, sorry. You don't need to go over.
All right, we're good with this one? Yeah, all right. Yep, all right. So let's do A, for instance. Supposing you know the integral from -2 to 2 of this function, and the integral from 0 to 5 of this function, so 0 is over here. What is the integral from 2 to 5? The integral from 2 to 5 of f, and I'll just write f is short for f of x dx, okay? The integral from 2 to 5, and I've got from -2 to 2, and from 0 to 5. So if I take from 0 to 5, now remember there's symmetry here, these two are equal. If I take from 0 to 5, and subtract from -2 to 2 half as much, I'll get there. Why? Because from 0 to 5 gives me what I want from 2 to 5, but I got to subtract this piece, right? And how do I subtract that piece? Well, I know from -2 to 2, and so if I take half of it away, I'm done. All right? And so that's basically what you're doing on all of these.
How would you know that there's symmetry?
What's that?
How would you know that it's symmetrical?
It's drawn pretty clearly symmetrical.
I mean, like, if it doesn't explicitly say.
If it doesn't state that, you just can't do the problem otherwise. You have to assume that, that it's drawn so clearly looking like it. Yeah.
No, I mean,
Look, I did a lousy job drawing it, but they did a better one in the book.
Okay.
Okay.
That one's pretty special.
All right, we good? Yes.
12.
12C, section section D, number 12.
Oh yeah, I kind of just ignored this one because I did this one.
Okay, so water is leaking out of a tank at R of T gallons per hour, where T is measured in hours, and it's got a graph for that. Okay. So C, part C, give an upper and lower estimate of the total amount of hour that leaks out in the first 2 hours. Again, when you're doing this from the graph, Katie, when you're doing this from the graph, you don't have to use like a formal Riemann sum. Just like there's a just figure about how many of these make a box, or actually just do do those things and take the area underneath the top here, the top there, the top there, and so forth. Okay? Just do an upper and a lower. It doesn't have to be specifically identical to the one that they use. Just pick an upper and a lower to get the estimate of the water from 0 to 2.
So wait, you're just guessing down the first?
Well, I mean, you're just using a height that goes above. So for this first one, I'd use the height, this is 2. And the next one, and I keep going with 2 until the graph definitely goes below the next one. I wouldn't make it too fine, okay? I would wait until the graph here.
Like,
Good.
see if it'll-
Oh, I didn't know how small to make it.
Photoshop.
Now I'm gonna have to wait, and it's Photoshop, which is the ever load. And shut up. All right, fine. I'll use the blackboard till this is finished. Are we all set then? Okay. All right. So here's the next thing. We can use integrals to create new functions, just like you can use the derivative to create a brand new function.
Oh no.
We can create new functions with integrals. Oh, good. It's on here. I can tell it.
Force quit.
Maybe not yet.
Uh-oh.
Command Option Escape.
Yeah.
What's that?
Command Option Escape.
Will that shut everything down though?
No,
No,
it's
no.
force quit of the application.
And Beach Ball.
Beach ball, we're done.
Already.
We're done.
It's gonna take a start. All right. So here we go. We're gonna create a new function, and I'm gonna start with a function, and I'll use the graph board. Yes, Photoshop, force quit.
Why is it on the old style watch?
I got
Force
confused.
quit. All right.
Ta-da.
So here's my function. Here's my function. All right.
Ta-da.
It's going to. I'm going to use to make it more visible. Each 2 boxes represents 1. So that's 1, 2, 3, 4, 5, 6. 2, 4, 6. Every 2 boxes represents 1. And I'll do the same on the y-axis. 2 boxes to represent 1. And here's my function f. It starts off at 1 and it goes horizontally until x equals 1. Then it goes down with a slope of -1 until at 3 it reaches -1. Then it goes horizontally till 5, and then after that it goes up at a slope of 1 until 6. This is my function f of x. What does it kind of look like if I were to continue that pattern? Just go up and over and down and over. Looks like, no, not sine, cosine, yeah. The squared off versions of sine and cosine. Sine and cosine are when you wrap around the unit circle and you trace the x and the y value of the point as it goes around the unit circle. If instead of doing the unit circle, you do a unit square, it goes from 1 to -1, and trace the x and the y values,
see how that's
you get
so
these
funny.
graphs. Well, this one
Unit
and the one
square.
that's like
No,
sine.
let's see how that's
So the x value is 1 while the distance you've traveled is 1. Then it shrinks to 0 and to -1 over the next 2 units. Shrinks to 0 and -1. Then it stays at -1 for the next 2 units. And then it goes back to 0, and if I were to continue, it'd go up to 1 and then stay at 1. And the period would be 8, because 8 is the, right, if this is 1 to -1, 8 is the perimeter of that. Just like 2 pi is the perimeter of that circle. So this is when you go back to the basic idea of sine and cosine, but you just vary it. You get 2 other graphs that are like cosine and sine, but they're squared off. I call them cousin of x and son of x, because they're related to
Oh
cousin
my
x,
God.
cosine and sine. So, all right. So this is cousin of x,
That was
and
why
we're
this
going
is
to
important.
define
We're done.
now.
That's the important
We're
part.
going to define 2 new functions. I'm going to start with one of them and help you make a table for it, and then you'll work with the other one. So capital F sub 0 of x is the integral from 0 to x of f of t dt. And Teddy, you asked why they changed the variables, and right now I'm calling this t just because it's sort of less confusing to make x also here and there, but actually you could just as fine do that. It's a dummy variable, doesn't matter what you put there. The x that's here just says this is the function that you're taking from 0 to wherever, and the other x is saying where you stop. Okay? So let's graph the function f sub 0 of x on the same axis as that. So let's start at 0. What's the value at 0? I'm going to use orange. At 0 is 0. Right? You're integrating from 0 to 0. You get nothing. Okay? What's the value at 1? What's the accumulation from 0 to 1?
1.
Yeah, because it's 1 this way and 1 that way. It's a square, right? So that's 1. What's the value at 2? Yeah, because you got a box and then you got a triangle, right? You got 1 and a half. 1 and a half of them. All right, so it's 1 and a half, so it takes it up to here. How about at 3? It's back to what?
1.
It's back to 1. Yeah, it's not 2 because this is negative. We're not doing area. We're doing accumulation.
We all
We're
suck
doing the
now.
integral. It doesn't force it to be positive anywhere. So this cancels that. So we're back to just the 1.
Oh,
All right.
God, it's fine.
Do you see how this goes?
Mhm.
All right. What is it doing in between? Between 0 and 1, is it going straight, concave down, concave up? What do you think?
Straight.
Concave
If
down.
I go
Concave down.
a third of the way, will I have covered a third of this area? If I go 1/3 of the way to 1,
Oh yeah.
will my accumulation be 1/3 of what I ended up?
Yeah.
So it's proportional, right?
Yeah.
So what's that make
Yeah,
it?
So it's
but
linear.
Linear.
Makes it a line, yeah.
it's the square side. Yeah.
I have a constant
Square
height.
side, not real
So
side.
every little bit of increase to the right is going to make my area increase the same amount. So my change in y for this orange graph over the change in x is going to be the same. Constant slope. How about from 1 to 2 though?
That'll concave down.
There's concave down because look, as I move to the right, I'm adding less and less area, right? So it's increasing less and less. So it's going up less and less steeply. And in fact, we know it's going to be horizontal here because there's symmetry here. It's going to turn around, isn't it? Now I'm adding more and more negative stuff, so it's dropping faster and faster. So it's still concave. All right, finish this graph, and let's go over something. Mike.
So it's gonna be linear over to the other corner, right? To like 5. It'll intersect again.
My scale was not
Makes
very
me
well
think of
drawn.
roller
Yeah,
coasters.
neither was mine. And then from there, it's
Yeah. Something like that.
Oh, that's awesome.
It's you, man. Over it on everyone.
what new math?
You math.
Wait, who are you videotaping this for?
You know, over it
Oh
on.
no.
These things.
Do you think they'd appreciate my face? No? I don't know who it's for.
I was gonna make a
They say.
I don't really know who. Kind of.
All right, we got it. Sounds like there's some conversation, like people are pretty much done.
Yeah.
So tell me how to continue this. What happens at 4? Where am I at 4?
0.
0 again, and how did it get there?
Linearly.
It's linear again, right?
Word.
Okay.
Linear.
Then at 5, where am I? -1, and how'd we get there?
Linear.
Linear again, yeah. And then at 6, where am I? -3/2, yep. And what's the concavity here?
Up.
Up. Any questions on how we got there? Everybody good with that? All right. So if you understand that, you can do the next one. The next one will be f sub. Let me see what I got here. Let's try f sub 3 of x. F sub 3 of x. You tell me what it should be. The integral of little f sub of t dt from
3 to x.
3 to x, right? The subscript is telling us where we start, but we're always going to wherever x now is. Which means, let's just say the first point on there, I'll use red for this one. For f sub 3, what do you get when you start at 0? It's the integral from 3 to 0. what's the integral from 3 to 0?
Negative.
That's the area here and there, but we're going right to left, so it's what?
Negative.
Negative 1, right? These two still cancel. This is now positive, that's now negative, but they still cancel. And this negative 1. So we start down here. All right? So go ahead and make the graph of this one. Again, connecting the appropriate points.
This is when I wish I had 50 colored pens.
Right? I'm already getting confused. Because I have two.
Well, you know it's going to be 0 at 3. So it's going to cross 0 at 3. Just
I
start
didn't
with
get
that.
why it was until just then.
Because x is the so it's like a function, right? So x is the variable that you plug in. So at 0, x is going to be 0 at 1. You get it?
But it's negative. And then at 1.
At 1, it's 0.
It's
It's 0.
Because you have, because you're going that way, so you add a positive 1.
Also because if you look at the graph from 1 to 3, it's 0.
2
Yeah.
is negative
Yeah.
half.
I hadn't thought this
Right?
Yeah, you're 0.
I was like, wait, no, guys, I'm pretty sure if you put 1.
No.
2. I can't tell which one's better.
Wait, is this just going to be translated down?
2.
Yeah.
Yeah.
It's 1.5.
Yeah, because it's just, yeah. Because it's effectively
Are you starting
subtracting.
to notice something?
Yep.
What do you notice?
No, it's 1.
Yeah, it's 1.
Translated down.
Wait,
It's
wait.
just a translation. This was 1 unit down, and so is everything else. Right? So this is 1 unit down.
Right.
So 1 unit is 2 boxes, so it's here. 2 boxes, 2 boxes, 2 boxes, 2 boxes. And it connects the same way.